And there's this formula, the Taylor von Neumann-Zidov formula, that explains point source explosions in an environment, and like say a nuclear blast out to like supernova. So I took this formula, and it like exactly describes the data. It's just fantastic that we're seeing these tiny little supernovas happening in our vessel 50,000 times a second.
And is that a fair way to think about this, like creating mini supernova?
Yeah, it's actually pretty similar. It's almost like very similar to a type 1a supernova, it turns out, where you kind of have an object that just fully evaporates and explodes apart. And when all that energy goes into the hydrogen gas, it produces a shock wave, a blast wave that comes flying out, which is basically the same thing if you look up in the night sky. There are these like remnant supernovas that you can see coming from space.
Using those energy calculations, they discovered they needed to flush the hydrogen at incredibly high speeds, around 360 kilometers per hour. That's more than a Category 5 hurricane, even if, those speeds are at low density. But 2012 came and went, and they still didn't have enough power. In fact, by 2013, ASML just reached 50 watts by shooting 50,000 tin droplets per second.
But this increased power came at a price, because more power means more heat. Heat that ends up slightly shifting the mirrors, resulting in misaligned light and misaligned chip layers. So Zeiss built a nervous system directly into the optics, robot-guided sensors that constantly measure the exact position and angle of each mirror, down to the nanometer and the pico-radian, which is absolutely insane.
So how accurate do we need to control this mirror? Now, one of the things you can do a thought experiment, and I can place a little laser on the side of this mirror. Then we go all the way to the moon, and we put a dime here. So then this light travels all the way here, and then with the accuracy I can control this mirror.
Yes.
I can decide whether I point to this side of the dime or
That's
whether
insane.
I point to this side of the dime.
What? That's crazy.
So you can see that the pointing accuracy is, that's also in picoradians. That is something very extreme.
This allowed them to control the light even when the power increased.
While Zeiss was doing a stellar job with the optics, ASML was still struggling with the power source. The problem was that the tin droplets were too dense, meaning that most of the emitted EUV light was still getting reabsorbed by the neutral atoms before it could ever reach the collector mirror.
The way we blasted the droplet was so not enough light, too much debris.
To make matters worse, they could see that about 10 years from now, they would need a new generation of machine, a high-NA EUV machine, essentially one with a larger optics system that could print smaller features. So what did they do? They decided to double down and invest in the next generation before they even got the current one to work.
The most doubtful period was in the beginning. So I started to work on this in 2012. By that time, EUV was not working. And there was this crazy idiot working on the next generation where we could not even make the EUV light in the first place.
Not only are you all in on EUV, you're doubling down even before you know if EUV is going to work.
Yes.
But to keep funding the development, they needed money, and lots of it. So they turned to the very people who needed this technology.
ASML reached out to its main customers. Okay, you want this technology for the next generation of chips? Well, you need to make us able to invest more by investing in us.
Intel invested around $4.1 billion, and Samsung and TSMC invested another $1.3 billion combined. So they can keep the research going, but with no product to show, customers were running out of patience.
We were crucified at every conference that the promises we made last year we were unable to live up to.
Yeah.
And they said, this is what you showed 2 years ago, this is what you showed last year, and this is what you're telling me this year, so why would I believe you?
They were getting desperate.
But this was, I think, about 2012 or 13. We were struggling to get the EUV power up. And Kinoshita visited us. I took him to dinner in a small town nearby, and across from the restaurant was a Maria chapel. And now, science, we have come to the limits of science. Hey, let's go for defined intervention. So we went to the chapel. So Kinoshita, just to be safe, lit 3 candles for the 3 suppliers that were pursuing EUV technology at the time. And lo and behold, and I have the data to prove it, there is a very strong correlation between us lighting the candle and power going up. It's not a causal effect, but there is a strong correlation.
The big idea was instead of hitting the droplet once, hit it twice.
One shot to hit the droplet and it expands in like a pancake shape. And then, only then have the second shot, the more powerful main pulse, where you evaporate the pancake and turn it into a plasma. This was a major breakthrough.
By changing the target from a droplet to a pancake, you got a larger surface area for the laser to vaporize, but without the cost of adding more debris or neutral atoms, because now the tin is vaporized all at once. By 2014, they finally managed to hit that coveted 100 watts mark. But improvements in multi-patterning with 193 nanometers now meant that EUV would only be useful if the source reached at least 200 watts and made 125 wafers per hour.
The source went from 100 to 200, but as the industry moved on, nobody waits for you. You know, they find other solutions. We had to catch up, so it was a moving goalpost.
One of the problems was, how do you perfectly time the laser so you hit each of these droplets?
So the analogy is a bit like a golf ball that you need to land in the hole 200 meters away. Not like land on the green, not bounce and then get in the hole, but like land in the hole every time. That's the level of precision that we need to deliver the droplets. Those droplets are traveling through this like maelstrom of hydrogen flow. The speeds are tremendously high. It's like shoot golf balls through a tornado. And then right when it lands at the hole, that's when it needs to get hit by the laser. So in order to basically track the droplets, for that we use laser curtains. And we can sort of look at when does the droplet pass through a laser curtain. Those scattered photons tell us basically when and where is the droplet. And then importantly tells us when to fire the laser. So we actually have to take into account how long will it take for the light pulse to hit the droplet after we send the pulse.
Now, by 2015, they were getting closer and closer to that coveted 200 watt mark, when all of a sudden, the ASML board members got summoned.
This was one of these decisive moments where our customers were really thin on patience. And Martin and other board members were summoned to Korea to show 200 watt. And they were really fed up with it. You know, you either show it now or you go away. And when they entered the plane, the experiment was still running. When they exited the plane, they had the first result demonstrating 200 watt. This is how close we came.
With the source power up, there was one final problem that had to be solved before they could begin manufacturing their machine.